It's Human in the Loop Mixup by Katie Collins, Umang, Bhatt, Weiyang, Ilia, Vihari, Piratla, and Ilia, Sucholutsky, Bradley Love, and Andrea Weller. And yes, please start your talk.
Great. So I'm Katie. I'm a first-year PhD student at the University of Cambridge. Apologies, I can't be there in person. I'm in England right now, but I'm excited to talk about our work, Human in the Loop Mixup, which is with a fantastic array of collaborators. To set the stage, I think it's worth reflecting on the broader ecosystem in which we develop and often try to deploy AI systems, which is usually in close concert with people. And of course, as an ML AI community, we very often focus on the model in ways that we can make the model better and give better predictions back to people for whatever tasks they might be doing. And in the UAI community, focusing in particular on ways to compute uncertainty, how we express, how we evaluate uncertainty, and give this back to people. But one area that this work extends and that I've personally been particularly excited about, I see Rory is also on the call and we've done some work, is looking at this other direction and thinking more carefully about what we get from people and how what we kind of give from people to the model impacts performance. And there's been a lot of great works in this direction, looking particularly at expressing human uncertainty, gathering human uncertainty, and giving this back to models in supervised learning settings. So a shout out to the paper that I alluded to, led by Ilia and Rory, that has a poster session tomorrow that's more on this question of uncertainty from people to models in supervised learning setting. But often this work that I've alluded to here focuses on kind of classical image data sets. So you would take CIFAR10, regular CIFAR10 images that have been sampled from out in the world, and you gather human uncertainty either by aggregating over many annotators as soft labels or gathering, say, uncertainty from each individual. And there's been works as we've been looking at that show that if you then train models on these kind of human uncertainty derived labels, that you can get lots of great boosts in performance in generalization, calibration, robustness. But there's so much other kind of data that we could train ML systems on beyond just images that are out in the real world. So what we wanted to focus on particularly here is synthetic data. And as I imagine everyone here knows, that synthetic data is becoming increasingly prominent, being generated at scale at a crazy pace, and increasingly being used as the data that we actually train the next round of models on. But there's a very important question, we think, with this rise of synthetic data as the training data, which is whether the labels that we're using when we use synthetic data in supervised learning settings actually coincides and aligns with human percepts. So we wanted to see how perceptually sensible are synthetic examples, and if they're not perceptually sensible, can we align model and human representations to get better performance? Or how does kind of aligning models and human representations in synthetic data change performance? And we focused in particular on the case of Mixup to study these questions. Now, the structure of this talk is that I'll first motivate why we chose Mixup. We heard the great oral earlier today on Mixup E, so highlighting of the popularity of Mixup. I'll then give a concrete example of how data is generated in Mixup, then go into the meat of our talk in our paper, which is on the data that we've collected from people over synthetic data and the elicitation interfaces that we constructed in order to elicit that data. And this is all available online for anyone who's interested. And then go into the computational experiments that we've done as a first pass of using these data to try to understand what happens when you attempt to align models more towards human representations. Then close by taking stock of what we've garnered so far, as well as highlighting the remaining puzzles. There's a lot that we still don't really know from our data and from these results. That'd be great to discuss in the poster session tomorrow, and then close with looking ahead with some exciting directions going forwards. Now, to start of why we chose Mixup, the three core reasons that underlie our choice of this is the first synthetic data paradigm that we studied. As we heard earlier in the Mixup E talk, Mixup is a very powerful regularization calibration technique, even though it's very simple in how you actually apply it in the way that you train models. You kind of do a simple convex combination of your training examples that we'll get into a bit when I show the example, but you kind of just linearly combine whatever your examples are in input space, and oftentimes you do that same linear combination in the output space. And we like this as a first generative model to study human perceptual alignment because it's quite simple, and we can get really rich inferences from people over the different parameters of this generative model. And third is that cognitive neuroscience work, and we have cites in the paper, suggests that there is going to be a misalignment in people from this linear mixing policy. So we had a sense that this was a ripe area to study human perceptual alignment on synthetic examples first. Now, I'll go briefly through the way that mix-up examples are constructed. Many of you might know this, but for those who don't, you have your classical data set that you would be using to train your model. In the CFAR setting, you might have examples of kind of noisy images that are one-hot encoded, that this is a bird, this is a truck, and usually you would then train your model on those examples. But in Mixup, you instead sample some mixing coefficient, usually from a beta distribution, and you then combine your usual training or your usual data set examples based on that mixing coefficient. And then the label that you would assign to this synthetically constructed image is a kind of linear combination of the original one-hot encodings. And you could do this for any number of mixing coefficients. And then you only ever train on those synthetically constructed examples. But it's not clear whether those X tildes, those constructed examples of these cars and bird combos, matches up with the label that's being applied. And again, because you're only ever training on these examples, this is the representation of your original data. So it's really important. We were thinking that these are perceptually aligned, or at least in some sense, we can interpret the labels and understand what the model is doing. Now, to address that first question of whether or not these synthetic examples are perceptually aligned, we designed two different elicitation frameworks. The first is that we showed people a series of these mixed images and asked them to give us the 50-50 point. So we said, kind of tell us which one is the midpoint between these two classes. And the second is that we had people see mixed examples and then tell us what the mixing coefficient is, so going beyond the 50-50 point. And we also got people's uncertainty in this. And for the sake of time, I'm just going to go very briefly into this first elicitation and focus more on the latter. But in the first case, what we did, as I said, is we gave people a series of mixed images between kind of a little less than 250 of these examples. And we did this over two different interface types to be sure that our results were robust. And what we see is that people in general actually endorsed the 50-50 point. So they were able to select the 50-50 point, but there's a good distribution over this. So we get uncertainty across participants, indicating that there is some systematic deviation between what people perceive and these kind of usually used 50-50 points in Mixup. And looking at an individual level, we have a lot of examples in our paper, but you can see that if you look at these, or if I look at these, I can definitely see that the 50-50 points not necessarily aligned consistently to what I would perceive to be a 50-50 mixture. So here, this in the middle is the actual 50-50 mixture between these images. And then on the sides are what people endorsed as the 50-50 point, which further indicates that there might be something missing, or at least not human perceptually aligned in the Mixup label policy. Now, what I found is the more interesting is that in the first case, we were looking just at the 50-50 point. We can actually look at a richer space of mixing coefficients. When you're running Mixup, you would usually be sampling any number between kind of 0 and 1 based on your distribution that you're using for the mixing factor. So we really wanted to study how people's percepts change over that full landscape of mixing coefficients. And to do this, we had people infer the data mixing coefficient. And to make this a bit more concrete, I think it's worth revisiting the generative process of Mixup examples in a kind of graphical model setting. So Y's here are the categories of the images in CFAR 10. That might be a dog, that you're sampling a dog image, X from the category, or a truck. You then have a mixing coefficient, lambda F here, that is then used to combine those images into a final synthetic example. And we show people the mixed example as well as the underlying categories. So blue here is kind of observed from the perspective of the participant. And we ask them what the underlying mixing coefficient, what they thought it was. And this is kind of averaging over all participants and overall examples, but we see that in aggregate, there is some blue here, the participants' kind of average responses, that there is some interesting nonlinearity that we observe, suggesting that the classical linear mixing policy in red is not exactly human perceptually aligned, which raises the question of what happens then if we train models instead on these human relabelings of these mixed examples. And to address this, we looked at a few different measures of not just generalization on held out examples, but also calibration, particularly expected calibration error, and robustness to adversarial attacks. And here we compared against the CFAR10, held out CFAR10 data, which is collected by Rory and Josh Peterson and others at Princeton, which is another representation of human uncertainty. And what we found was quite perplexing and is still perplexing, is that actually when you train models on the human relabelings, and I'll get into a bit of what we actually did because it was with an augmenting set, that performance actually got worse, which was not great from our end. We were hypothesizing that these models would be improved by training on kind of human relabelings. And we have some ideas about this I'm happy to discuss in the poster session, but I think this is an open question further, but for the sake of time, I'll jump to what we did next, which is then we hadn't only connected humans as relabelings, but also got a sense for people's uncertainty. So maybe we don't want to just be trusting people's inferred mixing coefficients at face value when people are actually unsure. So we'd also collected confidence in that inference. And we see is that people's confidence, their uncertainty tracks with the amount of mixing. So in the case when you mix these images more, people are much less sure in what the inference should be. So we wanted to see whether we thought that that'd be worth taking into account when relabeling. And we also see that there's a relationship between people's confidence and the underlying entropy measured by CFAR10H labels in the images that are being combined. So when we then relabel models based on people's confidence, we smooth the labels based on people's confidence and the relabelings, then we get performance gains. I should clarify that we've only looked at this in the CFAR10 setting in kind of contrived settings, and it's worth seeing whether these results and the value of human uncertainty in this case generalizes. But the central question that you might be thinking when looking at these results in this whole setup of human in the loop mix-up is whether this process is even scalable in any way. That one of the advantages of training models on synthetic data is that you can continually generate new examples. When you're running mix-up, you can continually sample a new mixing coefficient from a continuous distribution. You can pull any pairs of images or examples to combine them. And it's not reasonable to think that a person, a crowdsourced worker is going to be sitting there annotating each of them because there's an infinite number. So this got us thinking, are there better ways that we can build more generalizable human-aligned mix-up policies? And we've only taken a first pass at this, and I'd be very keen to discuss this further in discussion or poster session of other methods. But what we did in this first case is looked closer at the individual category pairs that we found in the data. So as I said, we were combining images of deers and trucks and cats and trucks and getting mixing coefficients there. So we can get out a kind of boundary of what sensible mixing policy might be between those categories. And what we did is we then fit a function to each of these category boundaries and use that instead as the mixing policy at a category level. So rather than the linear policy overall or individual relabelings, we would say for this deer truck case, when we combine a deer and a truck image at 0.75 mixing factor, we then could pull from whatever the fit function for deer truck was and get out, say, 0.9 is maybe that's the label policy that would be better aligned. And we see here is that there's basically no change in performance, which was interesting and also still perplexing. However, we view this as an encouraging step in the direction that is worth further studying the relationship between human perceptual alignment and model representations, and that it might be advantageous in other settings, say in a few-shot learning setting that Ilia, one of the co-authors, has been interested in particular, and Rory, rather than kind of just the cases that we studied here. There could be other advantages from a transparency standpoint that stakeholders might want to be able to understand what's in the data when you're using synthetic data, but a lot more to study here. And just to wrap up quickly, one other bit of cool results that we want to tease is this notion of going beyond just confidence in the inferred mixing coefficient, but questioning whether or not the label structure of mix-up labels themselves, or whether you're combining a deer and a truck, if that actually looks like a combination of a deer and a truck or something else entirely. So we've done a small scale study so far, but keen to do more, of actually asking people to infer soft labels over the entire categorical structure. So no longer telling them what the endpoints are that are being combined. And you can look at this image and might be quite confused, as participants were, but mix-up, this is actually a mix-up of a horse and a ship, which I need to continually remind myself of by looking at the underlying images. But participants, as you might see, not a horse and a ship in this mixed image, which suggests that there might be other better mix-up policies and related synthetic data mixing policies that are more human aligned, that account for human uncertainty in richer ways across the categorical landscape. Just to close, our data reveals that indeed it seems like there are some core misalignments between human percepts and the label and data mixing policies that are used in Mixup, which is not entirely unexpected, but nice to have empirical support for, and that relabeling with human perceptual judgments when accounting for uncertainty might be able to improve performance, but there's a lot more work that needs to be done to see how these results generalize to other settings and kind of scaled. And also addressing and beginning to address that question that you're discussing on scalability, especially when thinking about human-in-the-loop systems with synthetic data. So our data, our elicitation interfaces are available online. Please reach out if you have any questions on these. We hope that this can empower further work in this space. And personally, I'm very excited by the intersection of human uncertainty and model uncertainty. So happy to discuss this either at the post session or via email later. So thank you.
Great, thank you very much. Thank you very much for your great talk. Let's go to the discussion. Okay, so our discussion is online. I have to. Oh, sorry. Okay, yeah, this one. Yeah, okay. Yes, great. Yes, so discussion will be Jung Zhang. So please go ahead.
Yeah, hi everyone. This is Lin Jun from Rutgers. Can you share my slides, or do you have my slides? Oh, okay, great. Yeah, this is my slides. So first of all, I would like to congratulate the authors for this very nice work. So in this discussion, I will summarize the key takeaways from this paper and then raise a few comments that I have. So first of all, this paper considers taking human feedback into the mix-up data augmentation. The key idea is to replace the coefficient lambda g by the human inferred label, say lambda g hat. And there are three main messages that I got from the paper. First of all, the human guesses are very wild. So in the experiments, the authors found that the true lambda g and the human inferred lambda g hat can be very large. The second message I get is, so if we replace the lambda g by lambda g hat in the original mix-up datasets, the authors found that retraining over this human label dataset actually lead to worse performance than standard mix-up. However, a very interesting message 3 came up. If we take the human confidence, say WG, into account and create, say, a new YIG hat or YIG tilde, then this dataset, retraining over this dataset, will significantly boost the performance in terms of, say, generalization, adversarial robustness, and even calibration. So given those messages, I have a few follow-up questions. So first of all, the way of incorporating confidence seems quite essential here. In the paper, the author used some smoothness idea to incorporate confidence. So I wonder if there are more ways to incorporate this confidence, and maybe we can have more follow-up works to compare the different ways of incorporating this confidence. My second question is in terms of the human feedback solicitation procedure. So in this experiment, the authors provided the human labelers a few images with very low resolution. So this may increase the uncertainty. So I wonder if the authors choose some like high resolution images, how this change will affect the results. So if the humans are more confident in evaluating the image, will that help the model? The third question I have is, it's more related to the message 3, because we found that the performance is significantly boosted by incorporating the human confidence. So this is a little bit counterintuitive to me, because all the 3 metrics considered in this paper, say generalization and adversarial robustness and calibration, they are all objective metrics. So they are not, say, subjective like language model. Right? So in language model, there's a popular technique like ILHF, reinforcement learning with human feedback, which can align some subjective responses with human and therefore make human happy. But now, because all those metrics here are objective, I'm really curious, say, why alignment with human can improve those metrics. So one possible way to understand this further is if we try to align, say, with some feedback generated by those language models, like a GPT model. Can we see similar boosting? So if we see the difference, then we can further claim that, oh, the human really helps here. So that's all my discussion. And thank you again for this very nice work.
Thank you so much for the fantastic summary and the fantastic questions as well. Those are really great, especially the first one. One thing that I didn't touch on in the talk is whether or not people's confidence is even calibrated, that there's a lot of work in cognitive neuroscience and psychology showing that people are not necessarily calibrated when they give confidence. We just took people's we did a little bit of smoothing on people's confidence as we go into it in the supplement, but we haven't studied calibration of people's confidence much, even in that initial smoothing that we did on the labels. So that's one other way that confidence could be massaged before being incorporated. One other, I think it's also, one other thing I didn't touch on is that we have started to explore whether or not it's valuable to aggregate people's confidence, so or treat people's labels individually and maintain those. I imagine that there's lots of ways that confidence could be incorporated in beyond just smoothing over the whole landscape. Like I alluded to towards the end, we could also get confidence over the full space of possible categories. That is more manageable in CFAR 10, but if you go up to other large class cases like ImageNet, which gets to your second question, the methods might not be as scalable. I think the role of image resolution would play a huge factor in people's confidence. We didn't look at anything like ImageNet or other higher resolution yet, but I think that's a super interesting question that hopefully could be readily addressed through our elicitation interfaces, which are online. If anyone is interested in that, I'd be happy to also point out where you can kind of change in the directory of the images that are loaded in. But I think that's a really interesting question. To your third point, I don't have a clear answer yet, but I'd be very keen to discuss this further with anyone interested. It's a great question. I think part of it, even though it's different in a subjective objective sense, we were comparing against the CFAR 10H labels, which are beyond kind of one hot labels. So they already are soft labels that capture some sense of human uncertainty. So there's a chance that maybe like we were already matching to a human target label that was different than kind of just the usual one hot label that might have had an impact on that. It could also be another form of regularization that we were doing with the confidence-based smoothing that was helpful. But I think that there's a really interesting questions in that general direction of question 3. But yeah.
Great. Thank you again. Are there any questions from the audience? Maybe one short question can take. Yeah, over there.
Hello, can you hear me?
Yes.
So I was wondering, since you have sort of a human relabeling, did you just try distillation on the mix-up samples with either the same model or another model, like automated soft labels, and make a comparison there?
No, we did not, but I was realizing we should do that. So that'd be a very, very natural and important immediate next step. We have not done that yet. That's a good question.
Okay. Just because, yeah, like distillation pretty consistently boosts performance by, like, well, especially if you use a more powerful model, distillation pretty consistently boosts performance on CIFAR. So there, I don't know how that would compare to the human relabeling on the mix-up data. Yeah. Yes, that's a great question. One of the questions we were interested in that space is also whether the knowledge distillation, kind of the labels you would get from distillation, are more human aligned, and if that also coincides with the increase in performance. But those are we have not done that yet, and that's a good point that we should do and is interesting. Thank you. Thank you.
Okay, that ends our session. Let's thank again all speakers.